Hey guys, welcome back to Chapter 17 in Kinetics. Today we are going to dive a little bit deeper into the rate law, and we're going to look at what those orders mean for each reaction. We're going to look at a series of graphs to kind of understand this better, and we're going to look at how the concentration of the reactants affects the rate. So just as a reminder, the rate law was the following equation. So rate equals this equilibrium constant K, concentration of the reactants, and then this little n value that's an exponent, and that n value is the reaction order. And remember that the reaction order is going to tell us how rate depends on concentration. That's what we're going to dive into today. How does the rate depend on concentration of this reactant? When we're looking at individual reactants, so not the reaction as a whole, like the overall reaction rate, when we're looking at individual reaction rates for individual reactants, we will deal with 0, 1, or 2. That's it. 3 does exist. It's just super rare. So for our class, in this purpose, we'll deal with just 1, 2, and 0, 1, and 2. So let's dive in. As I go through these, there's going to be graphs that kind of help us understand what's going on. I'll make sure that I explain what the graphs mean, explain the units on the graph, but it's certainly something you're going to want to sit with and think about on your own time, not just watch me talk about it. So zero order, we're going to start with zero order. In a zero order reaction, the reaction rate is independent of the concentration of the reactant. Independent of concentration. So looking at our graph over here, along the bottom, let me get my pointer. Along the bottom, we've got concentration of A. So as we go from left to right, the concentration of A would increase left to right. Top to bottom, we've got rate of reaction. So down here, the rate is really slow. Up here, the rate would be really fast. In the middle, just is kind of moderate. Okay. So what I see here is as I increase the concentration of A, rate doesn't change. Increase concentration of A, rate doesn't change. Increase concentration of A, rate doesn't change. So it doesn't matter how much or how little of A I have, the rate for this particular equation will be constant. Now, what in the world would this look like? What's an example of that? I'm so glad you asked. An example would be something that undergoes sublimation. Fancy word. So that's something where we go straight from a solid to a gas. So an example of this would be dry ice. Okay, so I have a big old hunk of dry ice. I put it on my counter. That dry ice is going to start to sublime. It's going to go straight from a solid to a gas. As that block of ice gets smaller and smaller, the rate of that reaction is going to remain constant. So it doesn't matter if I have a teeny tiny little chip of dry ice or if I have a huge block of dry ice, it's going to go from a solid to a gas at the same rate, no matter what size it is. Okay, so that would be an example of a zero order reaction. This is a different type of graph, but I like to put it in here because it just helps us understand a little bit better. So in this graph, we've got time along the bottom. So over here on the left, time equals 0. Over here on the right is time has ticked away. Here we also have the concentration of A. So down here, low concentration. Up here, high concentration. I want you guys to focus on this zero order reaction. What we see is the rate of disappearance of A remains constant, right? That's a straight line. It's a constant straight line. So when I have a lot of A, the slope is right here. When I have a little bit of A, that slope remains the same. So what we see is the rate of disappearance, which is found in the slope. The rate of disappearance is constant no matter how much we have. That's our zero order reaction. What about a first order reaction? The rate of a first order reaction is directly proportional to the concentration of that reactant. So again, we see concentration of A increases from left to right, rate increases from top to bottom. And what we see here is I increase A, the rate increases. Increase the amount of A, the rate increases. Increase the amount of A, the rate increases. So there's this direct proportionality. So what do I mean by direct? Well, if I double the concentration, the rate is also going to double. If I triple the concentration, the rate is going to triple. Okay. If I talk about going the other way, so I cut the concentration in half, that rate is going to go down by a factor of 1/2. So it's this direct proportionality. Double concentration, double the rate. Okay. So in this, the rate is dependent upon concentration, and that dependence is a direct proportionality. Double, double, triple, triple. Looking at this graph again, we're going to focus on the red line here. Red line is first order. So what we're going to see is when we have a lot of our reactant, that slope is going to be very, very steep, right? So a lot of reactant, very fast rate. But what we're going to see is as the amount of our A goes down, that rate is going to also slow down, right? So if we cut the amount of A in half, the rate is also going to be cut in half. So as A disappears, the rate is going to slow down. And that's what we see with this line kind of curving off. The slope doesn't remain the same. The slope gets a little bit more shallow. That's the rate slowing down. The last one we're going to look at is a second order reaction. So the rate of a second order reaction is proportional to the square of the concentration. Okay. So again, the rate is dependent upon the concentration of A, and this time the dependence is an exponential dependence. So this is my best attempt at drawing an exponential curve. So what we see here is as the concentration of A goes up, the rate exponentially goes up. It goes up a lot. There's a very, very significant dependence here. So if I double the rate, if I double the concentration, the rate is going to go up by a factor of 4, 2 squared. If I triple the concentration, the rate is going to go up by a factor of 9, 3 squared. So the rate is going to just kind of take off on us as we make small changes to concentration. So here's kind of an example of that. So if I double the concentration, the rate is going to quadruple. And that comes from, if I double the concentration, the rate is going to go up by 2 squared, okay, which equals 4. That means the quadrupled. Okay. So again, rate is dependent upon the concentration, and it's an exponential dependence. If we go back to this graph, remember rate is kind of wrapped up in this line right here. So we're going to focus on the blue line. So when we have a lot of reactant, again, that slope's going to be very steep. But as we just cut out a little bit of our concentration, we see that rate kind of hits the brakes. It slows down a lot, right? So as A is disappearing, that rate is just going to kind of pump the brakes and slow down super, super fast on us. So there's a lot of correlation between the concentration of A and the rate. Another way to say that is the rate is very sensitive to changes in A. So little changes in A would result in big changes in the rate. So here's a graph that has all three of the graphs that we looked at kind of individually. So we looked at them individually like this. Now they're all together in one graph. So you have a visual kind of picture representation of the dependence of the concentration of A, how rate depends on that. So we change the concentration of A, what happens to rate? This is just kind of brief overview of these three. We have to determine orders experimentally. So what we're going to do in the next video is we're going to look at some data and be able to predict this is a first order, this is a second order, this is a zero order. I hope you guys found this helpful.